Okay, so we at least understand the basics. We understand that there exist slabs that are one way and two way, and there also exist slabs that are restrained. But the restrained slab focuses on both of them. So you could have a restrained slab that is one way. You could have a restrained slab that is two way. So what the restrained slab talks about majorly is uh, how how we are preventing, or if we are preventing the slab from rotating at given. So the restraint slab is majorly the degree of, how do I say this? The degree or the principle between restraint slabs and unrestrained slab is, if you're going to have any member as a slab and it is resting on beams, if it is not restrained, it means that you are going to be allowing these edges here to be deflected upwards. Okay, it means that at these edges here, you're going to be allowing them to be deflected outwards or upwards. But in real life, we are going to be providing beams at these edges. Okay, we are going to be providing beams at these edges, and what these beams do is that they prevent this slab from being uplifted at the edges. Okay, and if these slabs are being prevented from rotating at the edges, we are forcing it to have a lesser amount of degrees of freedom here. We are restraining it from basically deflecting upwards. What is going to happen is we are going to have torsional movements occurring in this region here. We're going to have Hogging movements occurring at these particular points. And if Hogging movements are going to be occurring, it means that you are going to be subjecting our member to tension at the top. All right. And that is the reason that for slab edges, we usually have reinforcement at these particular edges, because we are restraining them from having any type of uplift here. Okay, so that was one of the main reason things that I wanted us to read about. That was one of the main things that I wanted to read us about. Let me see if I have better explanation. Okay, I have this here. So continuous edge means that the slab is able to transfer load to the adjusted slab through that edge. Discontinuous edge means that the slab is unable to transfer load to the adjacent slab. So we're going to see this majorly when we come to design using the Excel sheet, and we are just going to come back to this to explain it when we get there. So this is just to paint a picture at this point, and then you're going to get there in a few. Then the book that I'm using for reference also talks about the restraint slabs, and this is what they said. So when a slab is provided with different edge conditions, so the edge conditions could be that this edge here is either continuous or discontinuous. If it is continuous, if you have either a beam or a slab or another slab going there, it means that the loads at this particular point here can be transmitted to the adjacent panel or to the adjacent beam there. Okay, and by transmitting it, it means that there are going to be just there are going to be Hogging moments here forming that are going to be preventing the slab from being uplifted at this particular point, or that are going to cause Hogging moments to appear at this point. So from that particular reason, we are going to end up requiring you are going to end up requiring or are going to end up creating tension at the top of the slab. Thus, you are going to require top reinforcement at these slab edges. Okay, so this one is majorly calculated or analyzed using the coefficient method, and we are going to go into that in just a few. So let's start with the software, and then you're going to get into all this. Okay, so when it comes to design to design in the software, we said there are two ways. So using the software, you can design the slab in two ways. The first one, the first one is uh, the first one, the first one is in using the theoretical method, and then the other one is in using the provided reinforcement. Okay, you're going to see the difference in just a few. So I'm going to start with the theoretical method. So for you to design for slabs using the theoretical method, remember these are just theoretical methods. They are just okay, they are just theoretical methods. Let me show you how you do that. So the first thing that you're going to do is to select a group of panels that you want to design. Okay. So what I'm going to start with, I'm going to start with floors at a, I'm going to start with slabs at any floor. So I'm going to go with the slabs at story 2. I'm going to expand story 2, and then I'm going to select my floors. Okay. Then after I select my floors, what I am going to do is I'm going to go to this portion here where the numbers are listed and copy them. Okay, so highlight them just to repeat. Go to floors. Okay, select all of them in one story, and then right click and select all of them. Then after you select all of them, go to where the numbers are listed and copy them. All right. Then after you do that, you are going to go to design. And then, as we said, there is two options. There is provided reinforcement and there is required reinforcement. So required reinforcement is more theoretical than provided reinforcement of RC members. So you're going to start with the required reinforcement. So there are two steps to calculating the required reinforcement. So since we are dealing with slabs, we are going to start here with required reinforcement of slab stroke wall options. So you click on this option, then you go to code parameters, and then you click on this page icon to create a new type of parameter. Okay, so I just repeat that. So if you want to see the theoretical results from your design, what you do is you go to design, then you click on required reinforcement of slabs stroke wall options. Okay. Then you go to code parameters to set the parameters. So if you are ready to work with a robot before, you are going to find that you only have one or two options here or none at all. So we need to create a new one. So to create a new one, you click on this page icon and you create it. So give it a name. I will call it a slab reinforcement or slab design options. Okay. Then once I call it slab design options, you're going to see that under general, we have the type of calculation required. All right. We have the type of calculation required for the members we have selected. So we have three types. We have bending and compression stroke tension. We have simple bending and compression stroke tension. Okay. For the suspended slabs, or the typical slabs that are going to be having in most residential buildings, we are going to go with simple bending. Okay, the type of reinforcement calculation, we are going to be going with simple bending. If you remember pretty well from your undergraduate studies, is that for these slabs here, they are exposed to shear forces. So we do not need to design for compression stroke tension. We would use bending plus compression stroke tension if we are dealing with something like a mat or something like shear walls. Okay, but for this particular option over here, we are going to stick with simple bending. Okay, and then for the main reinforcement direction, you have the option to select an axis you want the main reinforcement to run through, but I recommend you leave it as automatic. Okay, then you're going to go into materials. So to switch between the tabs, you just click at the top. So you go from general, then you go to materials. Then in the materials, you have the option to specify the materials. I always recommend I uncheck this option over here. and specify the material. So uncheck as in a structural model, uncheck it, then go to name and specify the concrete class that you require. Okay. The concrete class is going to have a big impact. It's going to have a big impact on the type of results that you get. It is going to have a big impact on the type of or on the nature of results that you get. So it's important that you select the right one. Okay, so select the one that you're going to be using on site. So I'll go with class 2530 and I will select it from here. And then in the cement class, I'll just go down slowly. So we have characteristic strength. So this is the characteristic strength that is associated with the class we selected. Remember, we are using the Eurocode. And when using the Eurocode, it uses the cylindrical strength and not the cube strength. All right. So the cylindrical strength is the first one, and the cube strength is the second one. So the Eurocode uses the cylindrical strength in its calculations. That's why you are seeing the characteristic strength here is 25. If you are using BS, the British standards, you're going to find that it uses the cube strength for, for its calculations. Okay. Then we have the cement class. You can have normal setting, rapid setting, or slow setting. So for the normal, for the cement class, you're going to go with normal. And then the structure class, I showed you where we get this in the Eurocode. We said for the typical structures, S1 is usually sufficient. And then we have the grade of rebar, of reinforcing steel. So the 500 here refers to the yield strength, the YK. Okay, it refers to the YK. So if you have to be sure what you are going to be using on site or what is available in your market. So if what is available in your market are rebars that have the characteristic strength of 500 newtons per millimeter squared, you need to select one with 500 here. So we typically go with C, and then we are good to go. So ensure this matches what you have on site. If you are using 450 or 460, you can be able to type it here. So to type it, you just left click here twice, and then you type it and click on OK. And it is going to go with that characteristic strength. But I want to have 500. So I'll just type 500 here and click OK. So if it was already 500 and you're using 500, you don't need to change that. Then you're going to go to SLS parameters. These are the serviceability limit states. So we have the allowable values for deflections. I'm not going to change anything here. I'm going to leave it as 30. But if you want to limit it, you can use the values of LY of the longest span divided by I think for slabs it's usually around 15 to 30 there. So you can use those fractions to calculate the allowable values, but I'm going to leave mine as 30 millimeters. Okay. And then in the environmental class, again, this is just from the Eurocode. I'm going to go with XC1 and here XC1. All right. And then in the reinforcement, you can get to select the type of bar you want to be used in the reinforcement. So you can select D12 or D10. So I can work with D10 for now. And then if they don't pass, I will just change them. All right. Then once I have this, I will just click on that, then close. All right. Then remember the numbers we copied. Now I will paste them here. I will paste them here and click on apply. And you're going to see that they have been applied. And to ensure that they have been applied, you could go to the plan view. We copied them from story 2. So I'll just scroll up to story 2 and you're going to see these symbols here. So once you see these symbols here, it means that those parameters have been added here. All right. And then once they have been added, just click on close. Okay. Click on close, then go to design. And now let's design. So remember at this point, we have only specified the code parameters to be used in the design. So we now want to design the slabs themselves. So what you do is you go to required reinforcement of RC slabs. And then here you have these parameter, these elements here. All right. So this is what it looks like. This is how this layout looks like. So we have gone to, let me repeat how we got here. We went to design, then we went to required reinforcement of RC slabs stroke walls. So on the left, this one is the most important one. This one is what is going to be directing the software on how you want those particular members or the design to be done. And then on the right, we have the ways in which we can view the results. All right. So this is what I want you to do. Uh, if you calculate all the panels that are listed here by default, it is going to calculate for all panels that are in your model. This one is going to take time, and it is totally not required. Okay, I'd say it's not required because if these slabs are typical, then there's no point of you designing all the floors. Just design for one floor and then use those results for the others. And that applies only to floors that have the same layout. So what you do here is you go to the list of panels, you click on these three dots, okay? Select none, then select the 175 millimeter ground floor slab. I'll just select all of them, anything 175 millimeters, because I'm not sure which name it is. So select them, then go to geometry, and then we are going to filter out. So I'm going to filter out, sorry. The easiest way to do this is to just paste the numbers. Let me paste the numbers we copied earlier on. I've seen a challenge with this. The challenge with the method I had started with would be in would be in filtering out the stories because we have a story one here, and then these typical flows are from story two to the top. So it would be a bit difficult to filter them out. So what you can do is from the numbers you copied, just highlight everything here and paste them. All right. Then after you paste them in the limit states, ensure you are using the correct uh, load combinations. So go to limit states and then click on these three dots. So let's start with ULS, go to combinations and select all your ULS combinations. And then once you do that, click on close so that your ULS combinations are used in the calculation. Then go to SLS, click on these three dots, go to combination, SLS, click on these two arrows, then close. And you're going to have those numbers or the code number listed here. All right. Then I'll click on calculate, let the software calculate, and I will give it a few some time. And then you're going to be getting the calculation status of all elements that have been designed. So this is the point where you can be able to tell which elements are not meeting the design checks. So what the software is checking for at this point, if the sections are sufficient for bending moments, shear force, and deflection, and even cracking. Okay. So for the members, you're going to see a few results here. So the first one is required types type as not required types are not ascribed to SLS combinations. Calculations may be incorrect. So that particular error usually arises. This particular error here, it's not an error, it's a calculation message, usually arises because we have not defined any value for the ACC limit state. So for this one, it's a non-issue because we are only required to calculate for ULS and SLS. And then for the admissible deflection value has been exceeded for panel number 332, 253, and 272. It means that for those particular panels, the amount of deflection you are getting is larger than what is allowed. Remember, we had an allowable deflection of 30 mm. Okay, so it means that the deflection for these three panels is larger than 30 millimeters. So when you get larger, let me note this down, and then you're going to look for those panels. So we have 332, 253, and 272. Yeah. So when a member fails by deflection, the way in which you can easily pass it is by increasing the depth of that particular panel. Okay, so I'll just close this, and then I will paste my numbers here, and I will click on view in new window so that I can view them in. Let me see. Let me see if I can find those slabs selected somewhere. I'm trying to look for the slabs. Let me see if. Okay, so let me just select them again. I will go to, I'll move from here, go to geometry, then select them. So I want to select my floors here. So I'll just select all my floors in the second story and copy them from right here. Okay. Then once I copy them, I will open a new window so that I can view these panels on their own. Then once I have this view, I'll just go to design. Remember, we had already set the slab options, so we do not need to set them again. But if you want to set them, just click on code parameters, select the slab options you just created, and paste the numbers there. Then click on apply, and they're going to be set. And you're going to see those symbols that had appeared. Then after you have that, go to design, and now go to required reinforcement of RC slab stroke walls. So once you're here, let me look for my view. So once you're here, this is what you need to do. First, select all these numbers here. Highlight all these numbers here in the list of panels. Okay. Highlight all these numbers and delete them. Then paste the numbers you had selected. Enter the limit states, and then click on calculate here. So calculate is right here. And then you're going to see the calculation status over here. All right, give it a moment to run, and then you'll see the type of results that you get. So what you're going to be getting majorly is uh, if the deflection has been passed, and then this one is going to be for everyone. The required types are not ascribed to SLS combinations. And the reason for this is because we have not assigned a code combination for ACC. So this one is going to be there. We are only interested in the ULS and the SLS. That's why this first one is appearing here. So let's wait for it to finish. It's going to design 32 panels. Okay, then I will close this, and I can close this once it's done. Then I will click on this option here. Okay, so here it is. I will select my panels, and then I'll paste my numbers here. Let me just paste them here. I don't know why my software is misbehaving, but I should be able to see my my I want to see my slabs, but I'm not having the option to see it. So let me see how I can select these. Filter from story. story. Okay. So once I do that, let me repeat how I was able to do that so that if anyone else faces the same challenge here, they will be able to find themselves in this particular view where they can be able to see their slabs. Okay. This was the challenge I was facing. I just wanted us to view this slab so that you can be able to read the results. So what I did is I went to, let me just repeat the entire process. So what you are going to do here is, let me just close this. Okay, so what we did is number one, we selected all floors. Okay, we selected all floors in one story. We are interested in story two. So I want us to select them so that we can use them for design. Then we went to design and required reinforcement of RC slab stroke walls. Then from there, now at this point, it's bringing it by default. But at first it was not. So probably it was just my software acting up. But if you find yourself in the same scenario, just click on none here. Then go to group over, go to geometry over here and filter them out. So first select, go to attributes, select your floors. If you've numbered them in a way that you cannot be able to filter them out, just check how you named your floor slab. Then once you have my 175 mm floor slab here. So once you have this, go to geometry and filter them out using the geometry. So we want to filter out from story number 3 all the way to the top story and click on minus. So you select them and then you click on minus. And then once you do that, just paste those numbers here. And then with that, run the calculation. It will only calculate for this particular panels over here, and it's going to give you it is going to give you the results. Okay, so you're going to get the calculation status over here. So we said the first one is because we did not assign a limit state for the ACC, which we do not require. At this time, you are only interested in the ULS and the SLS. And then for the admissible deflection value, this one is because of deflection. So for deflection, we majorly control it using the depth of a slab. All right. So you can either increase the depth of a slab or reduce the length of the panel. So you'll have to choose. You'll probably have to introduce a beam somewhere or use a different type of slab system. Okay, so let's go back to this. So once you have your members designed here, you're going to have these options here, the reinforcement here. So any results that you want to read, you're going to just click here. You just check them here. So you have the X negative, Y negative, X positive, and Y positive. Okay. So for you to understand these results, I will bring you to how do we call this? I will bring you to the coordinate system over here. So this is Y and this is X. So if you look at X negative, if you click on apply, check description and apply. So you can see the reinforcement areas at these particular points. So this is the reinforcement areas for the bars in the X negative direction. All right. So for the X negative direction, these are bars that are going in this particular manner at the bottom. And then Y negative are bars that are going in this direction upwards at the bottom. Then X positive are bars that are going in this. You can see the X. So these are bars going in this direction, in the X direction at the top. And then Y positive bars that are going in this direction at the top. So the first one, you can only visualize the areas. And you can see as soon as I type, as soon as I type, as soon as I click on any of them, the manner in which the graph looks like changes. Okay, so you can see, for example, the X positive, we have said these are bars, are top bars going in this direction. So you can see they are majorly at the areas where we have beams. Okay, you can see there are areas where we have beams and also at the edges. So at the edges, you're going to be, because these slabs are restrained. I hope you remember my explanation for restraint. So because these slabs are restrained in nature, you're going to be having hogging moments near the supports. So there's going to be development of uh, of of tension at the top. So you need top bars. Then you have the Y positive. So you can see the Y positive. So you can see where you need them. So the thing I like about using this method is it is a really good way of guiding you on how to detail. Okay. So when you want to detail your structure and to do your detailed drawings, you would need to know where you have your top bars going in certain directions. So someone may look at your detail and wonder why you have top bars over this entire panel. It might not make sense to them, but for you, you're going to be knowing that at this particular section over here, you had hogging moments, and that's why you have these areas here. For this area here, you have top bars even at the midspan of the slab, because this slab here, it has a very small, it has a very small it has a very small dimension in this direction as compared to the slabs on its edges. So what is going to be happening is that this slab is experiencing some deflection here at the center, and then near the support, it has hogging moments. And this slab as well, it's the same. It has deflection near the centers, and then near the support, it has some hogging moments. So this one here, because of its small dimension in this direction, is going to be majorly experiencing some uplift. Okay, so this one usually happens majorly in small panels that are adjacent or are sandwiched between two large panels. You find that they are experiencing some uplift. So due to that, they are going to develop some tension in the top, and you need to provide reinforcement for that. You can see how their Y negative bars look like, and they're just there. So where you have these zeros, it means that no reinforcement theoretically is required here. That's why this is theoretical. Okay, so from how the software has calculated this, it means that theoretically in the Y negative direction, Y negative is this direction here, that you do not need a reinforcement at this bottom here. Okay, so this is just theoretical. It's just a good way of understanding how your slab is behaving, but you would not typically use this for anything but your detailing, just to understand the slab. Then you can see the other information you can get from here are the areas of steel. We've done that. Then the spacing. So you have your spacing there. So you can see where the bars are majorly at. So these are the bars going in this direction. And then this is another thing that would affect your detailing. So when you're detailing, when you're doing your bottom bars for your slabs, you're going to find that in most cases, near the supports, you do not need to lap by much, because most of the reinforcement is not required in these areas. So for this one, you'd find that when lapping, it doesn't have to go into the next span by much. All you need to do is ensure that the lapping bars are 50 times the diameter of the bars. Okay, let me focus on design for now. So you have that. So this one is showing you the spacing. Okay. And then for you to understand how this spacing is, let me up to the close paint. So we have this panel over here. Okay. And then this is Y and this is X. Okay. Remember, this is Y and this is X. So for the bars running along Y, okay, for the bars running along Y, their spacing is going to be in this direction. So these bars along Y, they are running this manner, so their spacing is in between. Okay, so when you look at the spacing along the X direction, it means that it's for the bars running in this direction. And then for the spacing, say we have bars running in this direction. So this is the spacing. This is the spacing along Y. This is the spacing along Y. So if it's the spacing along Y, okay, if it's the spacing along Y, if it's a spacing along Y, it means, if it's a spacing along Y, it means that it's for bars running along X. Okay, so let me just pause there to see if we are together. Type a one if you are together. I keep losing my. Type a one if we are together. Let me see if we are together. Super. I hope I have not lost anyone. Type a two if I have lost you, or if I have confused you. Type a two. Okay, so I think we are together. I think I have not lost anyone, so I'll just proceed. So this is just the first method. Uh, yes, favor. You can increase the size of the steel, but remember, increasing the slabs usually use a lot of rebar. So if you use a lot of steel, if you go above uh bar diameter 12 for your slabs, your work is not going to your work your structure is going to be too expensive, and then it's going to look shoddy. Okay, it's going to look very shoddy if you give someone a detail for a slab and you are using T16 bars. That is something that is, I don't know, quite unheard of or quite rare, especially for the normal projects. So what you can do is, if you try, remember this is a solid slab. If you try your solid slabs and they are going to depths of 200 mm, probably 200 mm on the maximum side. If you start going above 200 mm, I would recommend uh, you I would recommend you look at different slab systems. Okay. So if you're designing your slabs and they start going above depths of 200 mm, you can start looking at different slab systems. Those are the hollow pots, those are the waffle slabs, the ribbed slabs. You can look at them because they allow for larger depths without being unnecessarily heavy or using too much rebar. So favor, at the start, you can increase the depth, and then for the depth, if it goes to above 200 for normal structures, I'd recommend you look at alternative slab systems, just the hollow pots or the waffle slabs, or the ribbed slabs. All right, so I will proceed. So those are just theoretical results. Those are what we have there. So I will go to how we do the design using the provided reinforcement, which is more in line with which is what you need from robots. Okay, this one is a beautiful way to guide you during detailing. It will guide you on how to place your rebars and the rest. All right. So to go back to the different layouts, this is something that you need to get accustomed to at this point. So for you to access the different layouts, you click on this drop down over here and then go to geometry. All right. So there are different layouts. You can see you have geometry, you have results, scale design, timber design, RC design, and tools. So these are layouts that you're going to be finding yourself a lot in the coming days. So I need you to learn or to get accustomed on how to maneuver through the various the various layouts. I used to struggle with this a lot. I remember there was a time I was quite lost and I had to close my work. I was keeping on closing the software so that I can come back here. But for you, just know that you can maneuver through the layouts using this. Okay, so I want us to design these slabs as well. Okay, this time we're going to be using provided reinforcements. And this one works differently because the software is going to be assigning the rebars for you. So to do that, you're going to go into floors. Okay, select floors for one story. Go with story two. Select them, select all of them, and then copy these numbers here. Okay, then you can press escape. Then once you press escape, sorry, don't unselect them. Select these numbers. Don't press escape. Go to design and then go to provided reinforcement of RC elements. So just to repeat that, you select the floors right here. You select all of them. Then you go to design and you go to provided reinforcement of RC elements. So I'll just click on OK. This one appears because I'm using one of uh, I'm using work that was submitted by one of you, and I do not have the file stored in the same folder as they did. So that's why that keeps on popping up on my end. So once you get here, it is going to be designing the slab for you. So this one is more practical. It is going to look at a lot. So we are going to look at these elements here. Okay. So we have some calculation status here. For example, I'm being told the program does not analyze punching at points to which inclined columns are joined. I hope this model does not have any inclined columns, but the software is just telling you that if your column is inclined, the program will not analyze punching at those particular points. But either way, we are not interested in punching at this point because our slab is supported by beams. So I'll just close this and zoom in. This is not what I expected. I'll just go back to geometry. Then so I want to select these floors here. So I'll select these floors. Then I'll go to member selection. Then I'll go to panels, attributes. I will select the stair waist and remove it. Okay. Or I could, let me find a better way of selecting this. I'll go to geometry. I will go to member selection over here. Then I will go to panels. Okay. Then I'm interested in the slab, in the 175 millimeter floor slab. So I'll select the 175 millimeter floor slab. Click on it, then click on these two arrows to select it. So this one is going to select all of them throughout the entire model. So to filter out the ones from the stories we do not need, so I'll click on story number 3, and then in the z-axis to story number 6, and then click on the minus sign. Then close. Then with that, I'll go to design and then provided reinforcement of RC elements. So I will just give it a minute to load. I'll just give it a minute to load and see what I have here. Okay. So it is loading. I think I have what I need. Okay, so Calculation will run automatically for all panels. That is okay. So I'll just close and I will proceed. So what you can see here is a slab for the entire, this is the entire floor plan. Okay, you can see the entire floor plan is here. It is different from what I had earlier. That's what I wanted to redo and confirm. So what we are going to be doing here is different from what we did before. So here we are going to be assigning parameters, and then we're going to run the design. So from here, we are going to be able to generate the design report. And then apart from generating the design report, we may also be able to see, we may also be able to see, we may also be able to see the rebars required. Okay, so to do that, all you need to do is first start at the top. So on my right, please look at my cursor. I am circling around with my cursor. So at the top right, you have calculation options. Then here you have the calculation option. So you just get to determine how the software calculates. So you have the amount of rebars. Majorly here, you're not going to be able to change a lot of things. What you're going to be confirming is if it is correct. So materials are to Eurocode. Uh, the class is class 2530. The characteristic strength for class 2530 is 25. So that is okay. Then for the reinforcement bars, these are the bars you want used in the design. So I'll check 10, 12, 10 and 12 only. You can also check 8. So I'll check 8, 10, and 12. All right. And then when selecting these bars, you need to select bars that are available in your local market. So in Kenya, we do not have class 14. We do not have diameter. We don't have diameter 14. We don't have diameter 18, and we don't have diameter 22. So I need to ensure that I select the diameters that are available in my market. Then in the wire fabrics, I don't need to select any of this. Then in the reinforcement for punching, I will leave it as this. We are going to select it when we are designing our mat foundation. Then you need to save it as, so that you can apply. Save it as, let's call this slab calculation options. I'll go with 2 because I have others, and then I'll click on OK. Then next, I'll go to story parameters. These are just in reference to the code. So I'll select XC1. You can say cannot select the structure class because we had already applied this. Okay, then I'll just save as, okay, and okay. Then the next thing is the reinforcement parameters. Now, this one is the important one. When you go to reinforcement patterns, ensure under reinforcement type, you have bars. Okay, this one is the most important one. Ensure under reinforcement patterns, what you have is bars, so that the software is going to reinforce your slab with bars. Okay, and then reinforcement segments, do it for the entire slab. Then bars. Okay, let's do it for single. Let's do it for entire slab. Sorry, then go to bars. The rest you can leave as they are. There, you don't need to change anything else. So for this one, just change bars. Then go to save as and save it as slab reinforcement patterns. Okay. Then click on OK. Then once you do that, all you need to do is see these calculations options over here. Click on calculate. Okay, so there are a few errors that you're going to be finding at this point here. So we are going to go over them. So we are going to see that for a certain panel, the minimum bar spacing has been exceeded. So the bars that are required for those particular bars there, they are they are they are exceeded. So you probably have a minimum spacing of allowable spacing of 3.5 centimeters. And what we have here, or what we need from the design, is 2 centimeters. Okay, so we are just going to see which panel that is. So I'll click on OK, and you can see this is the panel here. So you can see this is a small panel joined by joined or adjoined to larger panels. That's why it is requiring so much reinforcement. So for this panel here, what I'd recommend you do is when model part of the entire slab system, like this one here, so that you do not end up with funny reinforcement. Okay, that one is how you deal with that's how you deal with a minimum reinforcement. Just check how your slab has been modeled first. Okay, so if you have a very small panel and it is adjacent to larger panels, look at how it has been modeled. If it is a very small one, just change how it has been modeled and ensure that it is part of one larger slab. Then the other thing that you may do, if it's an entire slab that you are finding the spacing is very small. So the software has done the design, it has assigned the rebar, and it is finding that for particular panels, it requires a spacing of say 75, 100. It means that it is controlling things like deflection and cracking using reinforcement. Okay, so that's what it means. So when you're getting very small spacings, say 100, 75 mm, it means that your software is automatically controlling deflection and parameters such as deflection for the slabs using reinforcement. So what you do at that particular point is number one, if the slab depth is small, say 100, 150, I think 150 is the minimum that you can start with. 150, try increasing it to 175, 200, see if the situation resolves. All right, so this is what you have. So let's get to clear this up so that you can be able to visualize this. So let's go to reinforcement maps. Let's just make this a bit clearer. So I'm going to remove zone name, zone description. I can probably remove panel numbers, generate, and then let me see. Okay, I think this is now clearer. So you can see your slab here. You can see your slab here. This is the entire panel. So this panel here, now we need to just read the results. Just read the results. Okay. We need to read the results. So you can see the x negative. X negative are bars in this direction at the bottom. Okay, so you have your x negative bars, then you have your y negative bars, and you can see their spacing. So you can see you have a sketch. So click on y negative, and then click on generate. So you click on y negative, then you click on generate. And then when you zoom in, you're going to be able to see the bar. It is probably stretching from this point here to this point here. And then you can see that the spacing in this direction at the bottom is 200, and it's a 12 millimeter bar diameter. So this 452.39, this is the area of steel required, and then the 12 is the diameter of the bar, and the 240 is the spacing required. So you have 12 by 240 millimeters. So when you're detailing this, you may prefer to do with say 12 millimeters by 200 centimeters. Okay, or you could just use this 442.39 and then divide it by the area of a 10 millimeter bar and see what kind of space you would require. So let's assume I am doing a shift times. Okay, so you can do that, see the number of bars that you require for this particular area, and then divide it by 1,000. Divide the number of bars by one. Divide 1,000 by the number of bars so that you can get the reinforcement spacing. Okay, so that's how you can be able to just check that easily. Then you have the X positive. These are bars at the top. These are the top bars, so you can be able to see them in the Y positive. Okay, so this is how you are able to visualize this. And then after you've done your design, you'd be interested in generating a design report. So remember, whenever you design, you are going to need to you are going to need to generate a you're going to need to provide design calculations. Okay, so to provide the design calculations, what you do is you go to results, then you click on calculation notes. Then you ensure everything is checked. You can either check total or detailed. It doesn't have a big difference. Just have it as total and then click on OK. So this is going to generate the design report. There's something I want to show you. I want to show you something. So you're going to get this. Okay. This is not an error, and I want you to see something here. So you're being told that the AR is the AR is less than what is required. So you have the required reinforcement and the theoretical reinforcement. So you are being told that for certain points in your slab, for the top bars, especially, it is usually at the mid spans for the top bars and some bottom bars, the area required is less than what you need. So it means that for that particular panel, the area of steel is required is less. So what you need to do is just provide the minimum area of steel. Okay, so for that you could just use the area of steel other from other from other from other points of the slab. Okay, and then this is how the design report looks like. So for each panel, you're going to find that there are points that it does not require reinforcement. Okay, for each panel, you're going to find that there are points that it does not require reinforcement. And this has been done for all the panels. So this is what I was saying. You can look at this report here. You can look at this report here. It is quite long, and uh, it has some results that are not, say, easy to understand. So if you are to take this for approval, it would give you a lot of trouble because it is calculating loads and forces at each meshing point or at each node. So it's going to give you a lot of them that you do not need. So these cuts across all finite element softwares. So for the slabs, it's going to give you a lot of things, a lot of a lot of results for each node, which are not required just for approval. Okay, so what we do is that for the slabs, we do not use this report from the software. What we usually do is we provide a report using Excel. So we design our most critical slab using Excel. And then once we design that slab using Excel, we use those results. We use those results for the detailing of all panels, and then from there we print that Excel sheet and submit it for approval. Okay, so what we usually do is we provide uh, we provide we provide this report here for approval. You can see this one is easier. This one is easier to read as compared to the other one. The only caveat to using this one here is that you're going to be designing panel by panel. So let me go back to geometry. The only caveat to using the Excel sheet is that you're going to be designing panel by panel. So that becomes a challenge because you may want to know how the behavior of this panel here is affecting the behavior of this panel here. Like for example, when you are visualizing the theoretical results for this slab here, we found that we need top bars for this region here because we are going to be experiencing some uplifts in this region here. Okay. So for that reason, we needed top bars for this point here. So for that reason, for this one here, you may not be able to get that. So that's why you need to use the two tools together. So for the slabs alone, you're going to be providing a report using Excel, and it is to Eurocode. Okay, so I'll give you a minute to take some water, and then I just digest that, and then you're going to proceed. Okay, so I hope you are together. Is there anyone with a question with regards to using the software and Excel together? I will share the Excel file with you so that you can use it for your future projects as well. Anyone? Anyone with a question? If you are good, type a one so that I know we are together. Okay, I hope you are together. I hope you are all together. Someone else, please type a one. If you need clarification, type a two, or you could just unmute. Okay, so I'll assume you're together, then I can proceed. So I want us to design a panel using using the Excel sheet. But before we get there, I want you to look at this particular point here. We have we have uh, we have these how do we call this? Excuse me. We have this image here. It shows edges. We have edge one, edge two, edge three, and edge four. Okay, and then we are specifying if each edge is continuous or discontinuous. Okay, so when looking at if an edge is continuous or discontinuous, this is what we are looking at. So I'll just go back to. So I want to share this. I want you to look at this book. So we are looking at the slabs adjacent to a given panel. So if you look at case one, so case one is here, you have four edges continuous. So you have discontinuous on this edge, continuous on this edge, and this edge here. Then case two, you have one short edge discontinuous. So that is case two. You only have one edge continuous. And then for case four, you have one short edge discontinuous, and then the longer edge discontinuous as well. You have no panels going in this direction here. So this is what we were talking about earlier in the class. Let me see if I close this. So it means for a continuous edge, it means the slab is able to transfer load to the adjacent slab. So what is going to be appearing at that particular point there is you are going to be providing top bars at that particular point. And then you're going to find that at the edges where this slab is continuous, the Haugen moments here are going to be a bit less than they are when the slab is discontinuous. So when looking at the moment coefficients, for these panels here, you're going to find that for the panels where the edge is discontinuous, the moment coefficient for this point here is going to be larger as compared for when the slab is continuous. This is because this this member here or these moments here are going to kind of cancel out. So they become a bit less as compared to this one here. So this one is going to have a smaller effect on the slab as compared to this one. So that's majorly it. So what we do when using the Excel sheet is we look at our most critical panel. Okay, you can design for as many panels as you need, but what we usually do is we design for our most critical panel. So what you look at is your largest panel. So you can see that our largest panels are probably this one and this one. All right. So what we can do here is just measure them. Let's measure this distance here. That is 6 meters. And then the shorter span is the shorter span is 3.4 meters. So we need to design that. So what we are going to do is we are going to enter the dimensions. So we have the dimensions over here. The shorter span, LX, is for us 3.44 meters. And the longer span is 6 meters. And the height of our slab, our assumed height is 175 millimeters. And then from the report we had earlier on, I hope you remember this report. We're going to be building on this. So we are going to go to floor slabs. And what I want you to do is for the dead load, we said you are using 1.75. And then for the live load, we are using 1.75 for the living areas. So for the extra dead load, I'm going to have 1.75. And then for the impost load, I could even go with 3 just to show you. Okay. And then after that, you need to look at the materials and try it is in line with the class you are using. So if you are using class 25, have this as 25 newtons per millimeter squared or 25 MPa. And then we have 500 MPa for the steel. And then the density. So if you want to use 24 25, I think the difference is not that large here. So when you look at this, what is happening is this one is going to affect the weight of the structure. Okay. Then the other important thing here is at these values here. So if you remember the principles of uh, how do you call this type of design? I forget it. If you remember the principles of this, I forget this design. So we have these parameters here. We have these parameters here. So you'll see that for the strength of concrete, it's going to be divided by 1.5. And then for the strength of steel, it's going to be divided by 1.15. I am forgetting the name. I once I remember once it is back, I'm going to tell you. So it's just the principle in design. We tend to multiply the loads by a given factor. We multiply the dead loads and live loads by a given factor, and then we divide the strength of the materials by a given factor so that we can be safe. Because when we say we are going to be designing against a class of 25 newtons per millimeter squared, if there are errors in curing, if there are errors in mixing, then it's not going to achieve this. So to cater for that, we divide this value here by a given factor provided in the code. And then for steel, we divide it by a given factor as well. And then the other important thing here is just the loading and then the edge conditions. So you just look at your panel. So at your panel, we have only one edge being discontinuous. So you go to your Excel sheet. Where is that? So I will have edge 3 as continuous. So you just click and type, and then have edge 2 as discontinuous. And then as you change, you're going to see that the coefficient changes. So you can see short span 1, short span edge 1, if I have this coefficient as discontinuous, you're going to see that that it should reduce. They reduce. They are going to reduce. Let me see. So you can see if they're continuous there, the coefficients reduce, but once you have discontinuous edges, coefficients, the coefficients increase. Yeah, partial safety of factors. Thank you, Wadi. So these are the partial safety factors. Okay. You're going to see that there. Then once you have this, now the design bit with this is really easy because once you enter those parts, now you can be able to play around with the bars. So if you want to use 10 millimeter bars, you just type them here, and then you're going to see the spacing. So I'm just going to enter 10 everywhere. And then as I enter 10, this is what I want you to do. Uh, if you enter the diameter of the bar, you're going to see the spacing here. So if I enter a larger diameter, the spacing increases. So if I enter 8, you're going to see that the spacing reduces. If I enter, say, 10, the spacing increases. So you can see I need a spacing of 375 millimeters. And then that's majorly it. What the other things that you can look at are the reactions here, and then the spacings. So these are the spacings at the edges. So for the longer spans, you need to provide spacings at the edges at 400, 400 bottom two. And first, you have the short span and the long span. So for the long span, you have this span here. This is the long span. So I've been told for the bars along the short span, the bottom ones, you need T10 at 375 millimeters. And then for the long span, you need T10 at bottom two at 400 millimeters. You can see they are quite large. You can even say overestimate the loads, and you're going to see that for the slabs, they are typically easy to design for. They usually don't require a lot of rebars. The thing that you would be concerned with majorly is the deflection check. So if I was to reduce this to 150, so let me reduce the slab 150, you're going to see that it even becomes smaller. Okay, so let me do this. Let me increase this to 8, and then this to 5. Okay, so you can see it fails on minimum spacing. So it means I need to increase the depth. Okay, so on this direction by, it's not failing on this direction by deflection. But if you find yourself failing on a slab by deflection, you should be able to just increase the depth. Okay, so I'll just increase this to 175. And then you can see you have a valid design. So you just play around with the depth, and you play around with the depth and you play around with the depth and the sizes of the bars here. Okay, so you can see where it fails on deflection and the other elements here. You can increase the loads if you wish. For example, if you're designing for a roof, you can see what happens. So you can see if you increase the load, the minimum spacing fails and the deflection fails as well. So you could do 200, it is passes on deflection, but the minimum spacing still fails. So yeah, you have that, but that is quite out of scale. So you have that. Okay, so I'll remain with 6 and 3.44. That was just to show you how you play around with it, and they are good to go. Then after you have this, all you need to do is click on File and save it as. So let's open a new folder. Let's create a new folder for our design. So let me create a new folder. Let's call it Design Reports. Okay. So once you have this folder, all you need to do is go to your Excel file and save it as a PDF. So click on Save as, Desktop. We have Design Reports, and save it as a PDF. Okay, and save it as a PDF. Then once you save it as a PDF, you're going to get your design report there. This is what you're going to be submitting for approval. Okay, so this is what you're going to be doing going forward. So for the other reports, you're going to be generating them from the software. So for the design of the beams, the columns, the foundations, the shear walls, you're going to be generating them from the software. But for the design of the slabs, we are going to be using the Excel sheet, and that is something that you're going to carry on forward. Okay, so that's all. That's all with regards to designing slabs. Designing staircases follows the same process, but allow me not to go into it today. We are going to cover it together with a RAM. Okay, so unless anyone has a question, I'd like to adjourn the class at this point, and then I'm going to see you on Thursday for the design of beams.